Hello students. Today we will learn golden section search method. We use this method for unconstrained optimization. For single variable optimization, we can take inspiration from the bisection method that we used to find the root of a function. For the golden section search method, we need XL, the lower guess, we need XU, the upper guess, and the functional values at these 2 points. In the past, when we used the bisection method, we used to find the midpoint. We will not do the same here for the golden section search method. Remember, what is the motivation for optimization? We want to find the maximum or minimum or extrema, you can say. So the point is that a function is given to you and you want to optimize or you want to find the maximum functional value, the point x at which f of x will give you the maximum value. For the first iteration, what will you do? You will first check the length of the interval xu minus xl. Then how will you break it into 2 parts, L1 and L2? And how will you go to the next iteration? For this purpose, we will follow the following steps. The first step is that we will say let L0 is equal to L1 plus L2. Then we will take the ratio, all right. And for this, we will say that L2 by L1 is, let us call it capital R. Then we will obtain a quadratic equation from that ratio, and R is equal to 0.61803. All right. Next, we will say that we have D as this R times XU minus XL. To go to the next iterations, we will say X1 is XL plus D and X2 is XU minus D. In this way, we will find f of x1, then f of x2, all right. And we will, just like we do the bracketing, we will keep on breaking the subintervals into further subintervals, and the process will be based on the following key points. If f of x1 is greater than f of x2, then the domain of x to the left of x2 from xl to x2 can be eliminated because it does not contain the maximum. For this case, x2 becomes the new xl for the next round. Next, if f of x2 is greater than f of x1, then the domain of x to the right of x1 from both x1 to xu would have been eliminated. In this case, x1 becomes the new xu for the next round. So students, in this way, you will eliminate the parts or the patches or the subintervals, and you will keep the intervals where you are expecting that the function's maximum value holds. You can see here that we have subdivided the intervals. All right. So you can see that x1 is xl plus root 5 minus 1 by 2 xu minus xl. We can understand it with the help of an example. We can see that here we have a function f of x is equal to 2 sine x minus x squared by 10, with xl is equal to 0, xu is equal to 4. First step is to find d. Root 5 minus 1 by 2 times xu minus xl. Next step is to find x1 and x2. After that, find f of x1 and f of x2. Compare the two values. We can see that f of x2 is greater than f of x1. Therefore, we will select the relevant interval, the subinterval, and the process will continue till we get the maximum. Okay, you can see from this table, you have XL, you have XU, you have F of XL, you have F of XU, and then from these you have obtained, from the XL and XU, you have obtained X1 and X2. And students, please focus on the highlighted values. Why have we highlighted it? Because we are continuously changing the boundaries of these subintervals. Here you can see that, for example, let us look at the last iteration. What is happening here? 1.3901 is XL and 1.5279 is XU. All right, and then X1 is 1.4752 and X2 is 1.4427, right? And you can see that the functional values at X2 and X1, 1.7732, 1.7755. Can you see here? We have obtained the maximum values for functional values at these points, and these values are quite close to each other. And you can see here that 1.7647 is smaller than 1.7755. All right. So now students, you can see that with the help of the golden section search method, we can say that, note that the current maximum is highlighted for every iteration. After the 8th iteration, the maximum occurs at x is equal to 1.4227 with a function value of 1.7755. Thus, the result is converging on the true value 1.7757 at x is equal to 1.4276. All right. So now the question is that how will we write the M file for this algorithm? And for example, if the actual answer is not known to us, how will we stop? Because for example, after 10 iterations, 12 iterations, so what is the strategy? All right, and these slides I have obtained from the book of Stephen C. Chpara, because we are following the same book, the book from this author, for numerical computations and for numerical optimization. All right, so these slides are for numerical optimization, students, and we have learned the golden section search method, which is an unconstrained optimization method. And now let me take you to the M file. I have recently shared with you a Word document. All right. Now here, students, the point is that whenever you see function, okay, this means that I'm asking you to write a function or make an M file. Okay. So you can see that you have received this. Okay. And then you can see that until this line. Okay. Until the end, you will copy and then you will paste, and then students, please look at this M file carefully. You can see here that there is no red color here, so this means that we will be able to run this M file. If you miss to type this end, let's say, you can see the red color here in a minute, and then that means that this is not a valid M file. Okay, now the point is that uh, here I have called it golden search. So let me just call it golden section method. Okay, and let me save this M file. So the process is, click on the floppy button. If you are new to MATLAB, please click on the floppy button, select the MATLAB folder. Here you must get the same name as the function's name. Okay, so now you will save it. All right, now the point is that I want to apply this formula, or I want to apply this algorithm on the given function with the lower bound, with the upper bound, with the error estimate, and with the maximum number of iterations. All right. So now I'm going to take it to the command window. I will paste it here. I will put a percent sign here. Percent means that now I have it, but I cannot call it, right? So now students, I have already typed something for you here. And what is this F? I need to declare the F as well. So let me first declare the F. For example, let us talk about the exercise, and I have a function, this one. You can read it. You can see that at the rate of X means till now I have not informed MATLAB what is the input for X. For example, is X from 0 to 10 or something else? So for that reason, I've said that this is a handle. I'm saying at the rate of X, 4X minus 1.8X squared plus 1.2X cubed minus 0.3X4. Now I have declared the function F. Next, I will type here. Now remember that I want to type this function, okay, because I have recently saved the golden section method M file. So I want to call this function. I want to call this method. Now F is already given here. This function -2 is the lower bound, 4 is the upper bound, 0.01 is the error, 20 is the number of iterations. Now when I press enter, I can get my answer. All right. So please, now the project is to first to explain or explore, first explore it, then explain it to me what is happening in this M file, and then implement it on a problem, and then present your answer the same way as I have shared with you this problem, this solved problem. I believe now it is clear, very clear to you. And another thing that I want to mention here is that students, let me quickly read the M file for you. Here you can see R, which is square root of 5 minus 1 divided by 2. And here for the first iteration, I'm taking the lower value of X, I'm taking the upper value of X. Then as I have defined, we have defined, or let's say Stephen C. Chpara has defined in his book, the value, the formula D. We will follow the same pattern. This M file is nothing but just, like algorithm version of the same method. That's the golden section search method. So you can see the functional values at these 2 points. Now remember that an if loop is used here. Okay, let me mention here, if loop is used here. And remember that if this is the case, select F1. Else, that is, if that is not the case, then of course the F1 is less than F2, so or equal to F2, so then you will consider this part. All right, so remember that MATLAB always follow the syntax and the loops that you define. Next, you can see we have defined here the while loop, and we have said that next, when you go to the next iteration, because you are more concerned about the length of the interval, so you can see again for the new D, I have multiplied it with the old D. And next I have gone to the next iteration. So please study the M file. It is a long M file and there are different loops here. And you can see that we have used here for the error as well. We have said that this is EA, which is the absolute of XU minus XL divided by XOpt. So you can see that you have got some loops here, and you will stop when your error is less than the prescribed error, and when your a number of iterations is less than or equal to when you have prescribed the iterations, and you will not perform iterations more than the prescribed iterations. Okay, so now you can see here that, and then you will stop, you will say that max is the optimum value of X. So that max optimum value will appear in your command window. All right. Now, students, please try to go through every single part of this M file. For example, here I can see this part. So please define in your report what is meant by this. And you can always search for the MATLAB syntax at MathWorks website. That is very helpful. All right, so I wish you good luck and please solve one unique question. Every group will solve one unique question and then you will submit it to me. All right. Thank you very much.